Okay, in this video, we will talk about um, the multicollinearity in multiple linear regression. So, multi means more than one. Collinearity means, well, the linearity between the, let's say, the collaborators or between the independent variables. Please consider the following example. So, we will try to relate the length of an infant, okay, a newborn baby, to the variables of to the following four variables. Well, his or let's say its age, its length at birth, its weight at birth, and its chest size. Okay, so I will try to uh, the, try to find the relation between the length of a baby, right? Length of a baby, the relation between the length of a baby and his age in terms of age, sorry, its weight at birth, length at birth, and chest size at birth. Okay? So first, we will try to fit the model and just make some, let's say, analysis on the model and try to see if there's a multicollinearity between the x variables or not. So what does this mean? I will try to see whether there is a dependence, so we call the x variables are the independent variables. What does this mean? It means that the value of x, of one x, does not depend on the value of another x. Okay, so they should be independent. That's what the name independent implies. Okay? So we will try to see whether if there is a dependence, then what's its effect on the result. Okay? So this is my data. Okay, I have how many? Nine many data here. Okay, nine data here, nine babies. So for example, this is the first baby. His or her height is 57.5. So he's 78 days old. His length at birth was 48 centimeters. His weight at birth was 2.75, and his chest size was 29.5. So this what is that baby? So this baby is a huge one, right? So he's 5.5 kilos with 49 centimeters long and what? 36.5 centimeters chest size. And his length now is 67 centimeters. Okay? And this is the output for the model. Okay, so R square is almost full 0.99. Adjusted R square is 0.98, perfect. And when you look at this, just look at this one. So 0.69, that's the, so remember at each line, we have a test for the hypothesis. Okay. Oh, okay. So, well, each line has a each line is a hypothesis test, okay? And these p-values just refer to that hypothesis test. So it turns out that, well, you can reject the hypothesis in this line, you can reject it this line, you can reject it here, you can reject it here. The only thing that you cannot reject is this one, right? So this one says that, well, the only thing that, so when you add x3, it has a valuable contribution to the model. Okay, so let's try to fit a model with x3 only. Okay, x3, because adding x3 to the existing model. Okay, so you have x0 plus, sorry, beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 4 x4. Adding an x3 to this model, okay, is very, what is very, let's say, significant effect. Okay, it has a very significant effect. Okay, that's great. So let's run the model with x3 only. Okay, so this is the resulting model, right? The R square is 0.579. The adjusted R square is 0.519, and the MSE, which is the S square, it's almost 19. So in fact, this is nothing that I was expecting, right? So it was very significant adding it to the model, but it turns out that well, that's not something that is expected. Okay. Now let's try a model with x2 and x3. Okay, x2 and x3. Well, when you just fit a model with x2 and x3, well, the adjusted R squared is what? 0.979, which is almost 99%. Okay, the R squared is 99% as well. Its MSE is 0.509. Okay, which is, when you just go back, it was 19 here. Okay, it was 19, so this is smaller than 19. Okay, and this one, that's almost twice. Okay, that's almost twice times what? 0.519. Okay, right. 0.519, right? So again, this is something that we do not expect, right? Because it was the case that x3 was very significant, but x2 was not significant at all. But what we see here is very different. Okay, so this is due to what we call a multicollinearity. Well, some x's are linearly dependent to each other. Okay, so if you just go to Excel and if you just click the data analysis and click correlation there, it will just give you the correlation coefficient, okay, which is Rij, right? The metrics of the correlation coefficient, it turns out that x2, okay, and what? x2 and x1, right? And what? x2 and x1 are highly correlated. Okay, they are highly correlated. Okay, so they, and moreover, x3 and x4, they are highly correlated. So the thing is that, well, this Rij, it's between -1 and 1, and 1 means they are perfectly correlated, -1 means that they are, two variables are perfectly negatively correlated. So what does 1 mean? It means that if one variable just goes up, the other one surely goes up. Okay? What does -1 mean? It means that if one variable goes up, the other one for sure it goes down. Okay? So the values in between shows the let's say the amount of correlation, but if it is close to 0, it means that, well, they are not perfectly correlated. Okay. But here, x1 and x2, it turns out that it's 0.95. What does it mean? It means that, well, they are perfectly, almost perfectly correlated. And x3 and x4, if you just look at this again, they are very correlated. Okay. Hence, there is what we call a collinearity or multicollinearity in the data. Okay. So the collinearity screens the significance of the variables. So let me just go back. x1, x2, right? x1 and x2, just go back. So x1 and x2, the age of the baby and his or her length at birth, well, it seems that they are related. And x3 and x4, which is the weight and the chest size, they are related. Okay. So that's what we expected, right? So for example, just think about the car prices, okay? The car prices, okay? So for example, the age of the car, okay? The age of the car, let's take one variable x1 as age of the car and x2 as the kilometer of the car, okay? Kilometer traversed or traveled or traversed. Then what you expect is the age of the car clearly increases with the kilometer, or the kilometer clearly increases with the age of the car, right? They are just related to each other. So if you're just using x1 and x3 in your analysis, well, it's better to check whether they are correlated to each other or not. So we have a method to circumvent this problem, which we call as the stepwise regression, okay? Which has two main ingredients. The first one is the backward selection, and the second one is a forward selection. So as the name implies, in the forward selection, we will see it in the next slides, but in the forward selection, what we do is we just start with a with only intercept, okay? And then we just add, let's just see, let's assume we have this 3 betas, okay, in the previous one. So just pick the one which has the highest contribution, okay, and then continue with adding again B2 and B4, beta 4. Assume that, well, this one has the largest contribution, and then try to see whether, let me just put question marks here, which one to choose, and then which one to choose, beta 3. So this is beta 2 or beta 4, okay? So which one to choose? We will continue like this. In the backward selection, what we do is we just start with the full model, with the full model, and then try to see which one has the least contribution to the model, and then eliminate the one with the least contribution. Okay? So we will see them in the coming slide or in the coming video.